Most of what we're going to learn in chapter 2 are shortcut ways to find limits. To find derivatives without using limits. And we're also going to get exposed to some notation for derivatives that maybe it's kind of clunky. Um, I know that when I was a calc student at GCC, that I could take derivatives pretty nicely, but the symbolism was a little bit much for me. So, I'll take that into account that not every brief calculus student's going to get real comfortable with the more complex symbolism, but some of the basic symbolism we should all get used to. Anyways, depending on how a function is named, there are going to be different ways to describe the derivative and different ways to ask you to find the derivative. So, like if I wrote a function f of x equals 6x squared minus 7x plus 1, we learned in the last section that this symbol, with that little exponent, that little prime symbol, this represents the derivative of the function f of x. In chapter 1, I maybe wrote a sentence to ask you to find the derivative. I'd say, find the derivative of the function f of x, or find the equation that will help you get the slope of the tangent line, or find a formula for the instantaneous rate of change, all different ways of asking you to find the derivative. This would be a symbolic way to ask you to find the derivative. This is an efficient way. If I wrote this down, this means to find the derivative of the function f of x. If the variable isn't f, say in the function name isn't f and the variable is an x, I can still ask you to find a derivative using this little d notation. And the derivative of something written in function notation is almost exclusively written with that little prime symbol. So this symbol is a representation of the derivative of the function g of t, meaning t would be the variable to the right of the equal sign as opposed to x being the variable to the right of the equal sign. When we get functions that are solved for y or solved for z and not written using function notation, then we can still use that prime symbol to represent the derivative, or we could also use this symbol, and in chapter 4, this symbol is going to be, a little important. Now it's not so important. But if I had a function like y equals 3 to the 4x squared, putting a d dx next to the y, that's a symbolic way to ask you to find the derivative of this function. And when we write our answer, to the left of the equal sign, we could write a y with a prime just like we could with the f and the g, or we could write dy dx to symbolize this is the derivative of the function. Similarly, if I had an equation solved for z, I could, and you notice here there's a matchup here, that when this little denominator, the letter matches up the letter in the expression, for what it's worth. Not super important right now, but when we ask you symbolically to find a derivative, I'm not going to do a lot of asking you to find derivatives symbolically. I'm going to ask you to find derivatives using words. But this variable matches up with a variable in the problem to ask the question. We're using proper mathematics. Anyways, when I find the derivative of a function that's solved for y, I'd either write y prime or dy, and then in the denominator, whatever variable is to the right of the equal sign. So if I have an equation solved for z, to ask you to find the derivative symbolically, it's going to be d, and then in the denominator, d whatever variable's in the problem. And then the way to represent the answer, we could just write the z with a little exponent, or I could do d, the letter here, in the numerator, and then that letter in the denominator. That's just because we're going to get some symbols that you should be used to, and I just wanted to expose you to those. And as we go through the chapter, I'll use these symbols to represent derivatives consistently. This I won't use so much when I'm asking the question. This is just a way to ask you to find a derivative. And mostly I'm going to ask you to find derivatives using words. So we have just a handful of rules that will allow us to find derivatives without using limits, which is wonderful. And the first rule that we're going to learn is called the power rule. And the power rule basically says if you have a number, a coefficient, some real number, times a variable to the n power, that we can find the derivative of that function without using limits by multiplying the exponent by the coefficient and lowering the coefficient by 1. And this whole bunch of junk says it doesn't matter how the equation is written, whether it's written with an f of x or with a y, the derivative is going to be simply the same. And let me show you an example. So I started off with an example written with a function notation, and now I'm going to find its derivative using the power rule rather than using limits like we did in the last section. The derivative I find by multiplying the exponent, in this case 4, by the coefficient, in this case 5, and then I take the exponent and lower it by 1. This is what the formula says to do. The n, the exponent, gets multiplied by the a, the coefficient. So in this particular problem, the exponent is considered an n, the coefficient is considered an a. So this is the exponent n times the coefficient a equals x to the, subtract 1 from the exponent power, and the derivative of the function 5x to the 4th is 20x cubed. This power rule, to prove it, would be disastrous. It would take limits to prove the power rule, but we're not going to do that. When I took my calculus at GCC, in the 80s, I had Dr. Nadine Moore for my teacher, and she was really into doing every proof, which was fantastic for me. Not so fantastic for students that weren't going into theoretical math, because it probably took like 40 minutes of a 50-minute class to actually do a proof. And then all of a sudden she had no time to do the actual explaining how to use the rules. And now in this class, we're just going to explain how to use the rules. So now I'm going to find the derivative of 7x to the negative 2. And to find the derivative, this would be symbolically how I find the derivative. I'd say find the derivative of this function. But anyways, I'm just going to write the derivative down using the power rule. There's two ways to represent my derivative. I can write y prime for my derivative, or d y, and because the variable to the right of the equal sign is dx. So when I go to take a derivative, there's multiple ways to write the answer to the left of the equal sign. And there's probably multiple ways to simplify the answer to the right of the equal sign for a lot of the problems. But this problem, I'm just going to use the power rule. I'm going to take the exponent of negative 2, multiply it by the coefficient of 7, and I'm going to lower the exponent by 1. And now it's just algebra, which can be a little bit messy, but in this case, negative 2 times 7 is negative 14, and negative 2 minus 1 is negative 3. This is not the best version of the derivative, but it's a correct version of a derivative. Usually, we don't write answers with negative exponents, so I need to remember some trickery from intermediate algebra to make this negative exponent positive. It would be correct to say the derivative of the function is negative 14x to the negative 3 power. Would be equally correct to have the dy dx to the left of the equal sign as opposed to the y with a little prime. Usually I use this because it's just quicker to write. But to make this negative exponent positive, I'll create a fraction, leave the negative 14 in the numerator, and bring the x down to the denominator. That's in my intermediate algebra section P2. So if you wanted to see a better explanation rather than me just telling you what it is, you can watch my video for section P2 in intermediate algebra if you're wanting to get more detail on how to make negative exponents positive. Here I'm just going to use some trickery just to keep the lecture flowing. So next derivative that I wanted to take is the derivative of 6 times x to the 3/2 power. And how do I take derivatives? Using the power rule. The derivative I'm going to take, and I'm going to write the y prime symbol. I'd rather do that than the dy dx. I take the exponent, in this case it's 3/2, I multiply it by the coefficient, and I lower the exponent by 1. For the first multiplication, the 6 and the 3 will cancel, the 6 and the 2 will cancel, fraction will go away because the 2 will turn into a 1, the 6 divided by 2 is 3, so the coefficient of my answer is going to be 9, the 3 times 3 that's left. The exponent of my answer, I have to subtract and make the denominators the same. So this exponent of 1, or the subtraction of 1, I need to think of that 1 is as 1 over 1, and then multiply it by 2 over 2 to make the subtraction easy enough. So instead of doing 3/2 minus 1, I'm going to do 3/2 minus 1 written as 2/2. And this will give me the derivative is 9x to the 1/2 power. Again, fraction exponents are nice. Usually we turn fraction exponents into radicals. And this again is intermediate algebra. These two simplifications I'm about to do right now, the rewrites are buried in intermediate algebra or college algebra prep. To take that x to the 1/2 and write it with a radical sign, I write the radical. The denominator of the fraction exponent becomes the index. The numerator becomes part of the radicand. And when we're dealing with radical symbols, if there's no index written, it's assumed to be 2. And when I'm dealing with variables, if there's no exponent written, it's assumed to be 1. So both of these are correct answer. This is considered the preferred answer. Similarly, in the last problem, that negative exponent written as a positive exponent is preferred. In this problem, fraction exponents written as radicals are preferred way to write my derivatives. One last one, I think, and we'll move on to the next page. I have t, oops, better pull out another sheet of paper here. And again, this is just loads of algebra rules that we need to remember. We're kind of hitting them all at once, and then they'll just repeat over and over again through this chapter. So now I'm going to take the derivative. I could either write t prime, or I can write dt dx for my derivative. I like the prime, but this dt dx is going to come up in chapter 4, so I'll bring it up from time to time. It's always the d notation. In the numerator, it's the letter to the left of the equal sign. In the denominator, it's the letter to the right of the equal sign. And in order to do the derivative, using the power rule, I have to realize there's an implied exponent of 1 with that x. To do a derivative, it's exponent 1 times the coefficient 2 times the variable with the exponent lowered by 1. So it's 1 times 2, x to the 1 minus 1. 1 times 2 is 2, so then my coefficient's going to be 2. X to the 1 minus 1 gives me x to the 0 power, and x to the 0 power is equal to 1. So this is going to be 2 times 1, and the derivative, using whichever notation I want, the t prime or dt dx is going to be 2. So there's 3 big algebra tricks buried in this problem, all just using one basic rule. The power rule asks me to multiply the exponent by the coefficient, lower the exponent by 1. So the 3 kind of trickeries here, I need to be able to make negative exponents into fractions, I need to be able to make fractional exponents into radicals, and I need to know that 0 exponents are equal to 1. Eventually, we get comfortable enough that we start speeding through some derivatives. And the first kind of speed derivative is if I have a number times x to the first power. Without even thinking, I'm going to say the derivative is just the coefficient without doing the actual power rule. And I'll show you why it works and talk about what would happen. So this problem right here, if I asked you to find the derivative of y equals 7x, in order to use the power rule, I need to know what the exponent is. Since there wasn't an exponent written, there's an implied exponent of 1. So I'm going to always, when I go to use the power rule, be aware of what the exponent is. If it's not written, throw the 1 in that's implied. And now I'm going to take the derivative, which I could write dy dx, or I could write y prime. I'm going to multiply the exponent 1 by the coefficient 7. I'm going to lower the exponent by 1. So that now I'm going to get 1 times 7, which is 7, and then x to the 1 minus 1, which is x to the 0 power. This is going to be 7 times 1. So the derivative of my function, and this is what the rule is saying, that if you have a first power term, then derivative is its coefficient. I generally go straight from a problem that has an exponent of 1 to its derivative without doing any of this work. It's going to happen. This rule will happen every time. For instance, if I see this problem, g of t equals to 9t, I'm asking you to find the derivative of a first power term. The derivative of any first power term is just its coefficient. And the derivative of problem, the second example, is just going to be 9. If I wanted to emphasize and do this manually, I need to see the exponent of 1 to use the derivative. I need the power rule. I need to know what the exponent is. And I would say the derivative of g is going to be the exponent 1 times the coefficient of 9. And then I'm going to lower the exponent by 1. So it's going to be 1 times 9 as the coefficient, which is going to be 9, times t to the 0 power, because the exponent's going to come out to 0 when I subtract 1. And then I know that t to the 0 power, anything to the 0 power, is 1. So this becomes 9 times t to the 0, which is 9 times 1, which is 9. It's better to recognize, if you have a first power term, that its derivative is just its coefficient, rather than going through the math. Last problem I had written down here, f of x equals negative 3x. Again, this is a first power term. Without doing any work, I should realize that the derivative is just the coefficient. Rather than going through this process of multiplying the exponent by the coefficient, lowering the exponent by 1, creating an exponent of 0, I should immediately, anytime I see a first power term, go directly to the derivative without using the power rule. It's a shortcut that will work for the power rule every time. There's one more shortcut that's important, and that's the derivative of a constant. Any term that doesn't have a letter, its derivative is going to be 0. And on the sheet right here, I said, what's the derivative of y equal to 7? 7's a constant. It's going to be 0. That's what this rule says. If I'm given a constant and I'm asked to take the derivative of it, the derivative is going to be 0. And in order to show you that the derivative of a constant is 0, well, I can't use the power rule how this is written. I need to rewrite it to be the same, or to be equal, but to be usable for the power rule. Writing 7 as 7 times x to the 0, these are equal to each other, because this 7 times x to the 0 is really just 7 times 1, because x to the 0 is 1. So now, if I just didn't want to believe that the derivative of y equal to 7 is y prime equal to 0, I'd have to use this strategy of rewriting. And now I can take the derivative by multiplying the exponent 0 times the coefficient 7, and then I can lower the exponent by 1. This is going to give me 0 times x to the negative 1 power, because 0 times 7 is 0. And then 0 times x to the negative 1 is still 0. So I can say the derivative, using the prime notation or using the dy dx notation, is 0. And this is another thing that I shouldn't use algebra for. If I see a constant, a number without a letter, its derivative is automatically 0. So similarly, I did the g notation. If I want to find the derivative of the constant 9, it's going to be 0. In order to get the derivative with doing algebra, and rather than just going, oh, this is a constant, its derivative is going to be 0, you'd have to rewrite it. You'd have to rewrite the problem as 9 times, in this case, t to the 0 power, because the variable is t. Now that I have it written equal to the original problem, but in a place I could use the power rule, I can find the derivative by putting the little prime symbol taking the exponent 0, multiplying it by the coefficient 9, and then lower the exponent by 1. This is going to give me the derivative is 0 times 9, which is 0, times t to the 0 minus 1, which is t to the negative 1 power. And then 0 times t to the negative 1, it's also just 0. So these are two tricks. If we have a x to the first power term, the derivative is its coefficient. If we have a constant, its derivative is 0. I shouldn't do any algebra to get there. On the third example that I wrote, asking you to find the derivative of f of x equals negative 3, because that's a constant, I shouldn't do any of this work. I should just know that the derivative of any constant is 0. As similarly, I should know that the derivative of any first power term is 1. It's going to save myself quite a bit of work. When we're asked to find the derivative of a expression that has a sum, or a function that has a sum, I just take the derivative of each term independently. That's what this rule says here. If there's a sum of terms and I'm asked to find the derivative, I just do the derivative separately, of each term separately. So if I'm asked to find the derivative of 7x squared plus 6, I just find the derivative of 7x squared, and I find the derivative of 6, and I keep the plus sign between. So the derivative of 7x squared plus 6x, I'm going to write dy dx just because that's the less common way to write this, and just to get us used to seeing it. I'm going to do the derivative of 7x squared, which is just going to be 2 times 7, x to the 2 minus 1, plus the derivative of 6x. 6x is the first power term. Its derivative is just its coefficient of 6 using the shortcut. And so the derivative of this, 7x squared plus 6x, is going to be 14x to the first plus 6. I usually don't factor derivatives unless there's like a common factor of x, or unless I'm going to do something with the derivative that involves me setting it equal to 0. So I would call this the derivative of that function. And again, if you have a function that's written as a sum of terms, you just do the individual derivatives to find the derivative of the sum. Similarly, if you have a subtraction of terms, to do the derivative, you just take the derivative of each and keep the subtraction between. This I was cutting and pasting and apparently didn't do so well on my editing. But if there's a minus, let me make a different example. If there's a minus, like if I gave you a function, I'll make up a new function. Let me do g of t equals 8t cubed minus 24t squared minus 7. If there's a difference and I want to find the derivative, I do the derivative one term at a time. That's what this rule allows me to do. The first term, I'm going to start speeding this up. I'm going to take its derivative by going 3 times 8 and getting 24. I'm going to lower the exponent by 1 and get a 2. So the derivative of my first term, 3 times 8 is 24. Lower the exponent by 1, get t squared. Bring down the minus. For the second term, the derivative, I go 2 times 24, which is 48. Lower the exponent by 1 to get 1, but I probably really shouldn't write that 1. And the last term's a constant, its derivative is 0. So the derivative of this function that has a couple of subtractions in it, I just do the individual terms, and get the derivative is 24t squared minus 48t. It only works for addition and subtraction. For multiplication, I just can't take the derivative and multiply them together. The rules for multiplication derivatives and problems with division derivatives are more complicated. We do those in section 2.2. The rest of what we're going to need to push through in this section is getting the problems that aren't necessarily set up to do the power rule derivative and rewrite them for the power rule. And there's about 3 tricks that we need to learn. And the first trick that we're going to need to learn, if we have a number over x to some power, And let me just do a different example. If I gave you something like this, g of t equals 5 over t to the third power, if I wanted to take the derivative of this, it's not set up for the power rule. The power rule needs everything to be written as coefficient times a variable to some power. I need to know the ability, I need to have the ability to rewrite the problem to use this power rule. And the way that I'm going to rewrite this is I'm going to take the fraction, make it a non-fraction by making the exponent negative. So 5 over t cubed is the same as 5t to the negative 3. And now I can take the derivative. So I'm going to write my little prime symbol. I'm going to multiply the exponent negative 3 by the coefficient 5. I'm going to lower the exponent by 1. This you should do in your head and not show this step. You should go directly to this step, that the derivative is negative 15 t to the negative 4th, and then use the trick to go backwards to make the negative exponent positive by creating a fraction. The negative 15 is going to stay in the numerator of that fraction, and then the t to the negative 4th is going to go back down to the denominator, and the exponent will be positive. This example over here is just another example. This problem right here, I needed to think of it as 2 over x to the first power, rewrite it with a negative exponent, and then multiply the exponent by the coefficient, lower the exponent by 1 to help me be able to write my derivative, and then make the negative exponent positive. When there's multiplication, there is a special rule to do the derivative when there's multiplication, but we don't get that right yet. For right now, if there's multiplication, I need to get rid of the multiplication before I could take the derivative. So to find the derivative of 3x plus 5 times 2x minus 3, I need to do the multiplication, which is going to be foiling before I take the derivative. So I'm going to do firsts 3x times 2x, which is 6x squared. Outers 3x times minus 3, which is minus 9x. Inners 5 times 2x, which is plus 10x. Lasts 5 times minus 3, which is minus 15. Combine the minus 9x and positive 10x and get positive 1x. So this is not the derivative. Notice I haven't written the little prime symbol yet because I haven't done the rule of multiplying the exponent by the coefficient, lowering the exponent by 1. Now let me take the derivative. So I'm going to write the prime symbol, and I'm going to do it in my head. First term, 6x squared, I'm going to take the 2, multiply it by the 6, and get a 12. And I'm going to lower the exponent and get an x to the first power. Shouldn't write the 1, but it's okay. Second term is a first power term. The derivative of any first power term is just its coefficient without an x. That's a shortcut that we'll use a lot and need to get good at it. Last term is a constant. The derivative of any constant is 0. This is using the 2 tricks that I'm going to use over and over again. And rewriting that, I get the derivative is 12x plus 1. And notice I started writing the little prime symbol as soon as I applied the rule multiplying the exponent by the coefficient, lowering the exponent by 1, or using the shortcut rules. That's when I start writing the prime symbol. These first 3 steps, that's just algebra. That's just foiling and combining like terms. That's not taking a derivative, so I didn't write the prime symbol on my first 3 lines. One more, maybe a couple more, and then we'll get into a part 2 where I actually do the homework. So there is a special rule to take derivatives of fractions. We don't have that special rule yet, and so I have to write fractions very carefully for us to be able to rewrite them to use the power rule. So in this particular example, I have a fraction and the denominator is a monomial. I don't know how to take the derivatives of fractions that have x's in the denominator at this point. So I'm going to take the problem and rewrite it by taking each term in the numerator and separately writing it over the denominator. So I get 4x cubed over 2x and 6x squared over 2x. The first fraction, 4x cubed over 2x, I need to reduce it. And 4x cubed over 2x, it's going to have a variable of x squared because the numerator has 3 x's, the denominator has 1. I could cancel one of the x's and be left with 2. And then the 4 over 2 is 2. So this first fraction, 4 over x cubed divided by 2x, reduces to 2x squared because the 4 over 2 reduces to 2, and I'm left with an x squared. The second fraction, 6x squared over 2x, I can cancel one of the x's from the x squared with the x in the denominator. The 6 over 2 reduces to 3. The second fraction is going to reduce to 3x. All this is not a derivative, so I haven't written a prime symbol. Now I'm going to do the derivative. And how do I do the derivative? Well, for the first bit, I'm going to multiply the exponent 2 by the coefficient 2. I get 2 times 2 is 4. Lower the exponent from 2 to 1. Second term is a first power term. The derivative of any first power term is just its coefficient. And then I clean up my answer. The answer is going to be 4x plus 3. Finally, one last problem, and we'll break for a part 2 to get to the homework. This is all the theory, and maybe after me just doing the theory, you might be able to do all the homework without my video. So you might want to just try the homework, but let me do this last example. So if I give you a function, in this case 3x squared minus 4x plus 5, I'm asked first to find the slope of a tangent line and then find an equation of a tangent line at x equal to 2. Plugging numbers values of x's into derivatives gives me the slope of a tangent line. The slope of a tangent line at a value for x can be found by substituting the value of x into the derivative. So I'm going to find the derivative. For this function, f of x that's given, let me find its derivative. For the first term, I'm going to go 2 times 3 and get a 6. I'm going to lower its exponent from 2 to 1 and get 6x to the first. The second term, its derivative is just going to be 4 because it's a first power term. Its derivative is its coefficient, technically a minus 4 because the minus in front. And the third term is a constant. Its derivative is 0. So the derivative of this function is 6x minus 4. If I take a value of x and plug it into a derivative, it gives me the slope of the tangent line at that value of x. So in part A, where it asks me to find the slope of a tangent line at x equal to 2, I need to take that x equal to 2 and plug it into the derivative. When I take the derivative and I plug 2 in for x, which is a given value of x, what I'm getting is a slope of a tangent line. And in this case, this is going to be 12 minus 4, which is 8. So the slope of the tangent line when x is 2 is going to be 8. M is 8. So next I want to find an equation of a line. And in order to find an equation of a line, you need a full point and a slope. What I have right now is I have the x coordinate of a point that was given to me in the instructions, and I have the slope. I don't have a y coordinate of a point. I need to get the y coordinate of the point, and we did this in the last chapter, but maybe it wasn't so clear. Hopefully it becomes more clear now. To get the y coordinate of the point, I'm using the original function. To get the slope, I'm using the derivative. So I'm going to take this value of x equal to 2, plug it into both 2's in the original function. I'll get 3 times 2 squared, for plugging 2 in for that x, minus 4 times 2 plus 5. 3 times 2 squared is 3 times 4, which is going to be 12. And then minus 4 times 2 is minus 8 plus 5. If I did my math right when I typed this up, that gives me the y coordinate of the point is 9. So I started off with the x coordinate of the point being given at 2. Now I've figured out the y coordinate of the point is 9 by plugging 2 into the original function. In part A, I found the slope of the tangent line when x equals to 2 is 8 by plugging the number into the derivative. Now I have a point and a slope. I'm just going to use the y minus the y coordinate of the point equals the slope times x minus the x coordinate of the point to get my equation of my tangent line. There are other ways to get the equation of the tangent line. This is just the way I prefer. So algebraically, this is going to give me y minus 9 equals 8x minus 16, and then add 9 and add 9. This is going to give me y equals 8x minus 7, and that's the answer to part B. So for part A, my slope of my tangent line is 8. For part B, the equation of the tangent line when x is equal to 2 is y equal to 8x minus 7. In the last chapter, I showed a bunch of graphs of these tangent lines. It might have been nice to do that now, but I didn't ask for it, and it's not necessary to show it, so I won't show it here. The rest of what we need to do for section 2.1 is just the homework, and I'll put that in a separate video. And I think there's probably more problems in this section than you need to do for homework. So I scrunched down the homework. Rather than doing all 45 odd numbered problems, I minimized the homework. And so you don't have to do every odd numbered problem in this section, but if you feel you need to do every odd numbered problem, then do it. There's nothing wrong with doing more than I suggest.